Raise your hand if you cannot hear. That's the first quick question of the day. There will be more. So I have a short slide deck for you today and entertain questions at the end as well. And then a couple of spreadsheets that I want to show you. One based on actual customer reality, if you like, and another projecting outward into the exabyte era, which we are now in, by the way. I don't think I have to remind any of you that we are in an exabyte era. No question about it. So I'm going to cover a little bit of 3D NAND. Again, happy to take questions at the end of it. If you have questions on 3D crosspoint and all that, I'm happy to entertain that too, although this talk is not really about crosspoint. Although, as you well know, it is a form of non-volatile memory and a rather interesting one at that. So let's do this. So kind of 3D NAND 101, if you like. This is not certainly exclusive to my company. There are several companies that now manufacture this in various stages of production, in various layers, in various geometries and lithographies and whatnot. So we announced this last year and are now in full production of 3D NAND, and the first drive, or SSD, with a Micron label. There are other labels, of course, that is made of this material. So first generation 3D NAND for us. Absolutely density counts. I'm going to spend some time talking about density. Today our 3D NAND density, first things first, it's a 32 layer technology, right? And then we have MLC, or 2-bit per cell, TLC, 3-bit per cell versions of that. The MLC version is 256 gigabits. In a die, and then the TLC version, as you might expect in the ratio of 3 to 2, is 384 gigabits, and then again that's with 32 layer. So we're very happy with that, manufacturing it in a couple of fabs around the world. And as the previous speaker mentioned, there are all sorts of advantages that I probably don't have to bore you with this technology. You know, literally, and I'll get to a slide here in a bit. This is a little interesting. It's a bit too marketing from my taste. I'm not a marketing guy. I wrote code for a living for a long time. But it gives you the sense of scale on geometries and where 3D and first generation 3D NAND is in terms of, you know, how many die do I need to form a 32 gigabyte repository, right? And at 50, you can see the progression over time. Starting about 10 years ago or so, you know, 50 nanometer, we needed 16 die. You could package them 16 high or 4 quad packages, take your pick. But we needed that many just to get 32 gigabytes of MLC storage. TLC is, of course, a different chart, but this is MLC for you. And then, you know, we went 34 nanometer, 2520, and now here we are at 3D with a single die holding that much. This is an interesting one. So why do 3D NAND? It must seem obvious to all of us now, but 5 years ago it really didn't. You know, we were on the shrink the lithography train. And that train basically, I can make several, the jokes write themselves after this point. But we're done, right? We're not shrinking. You can attempt to go down towards 10 nanometer, and it's a fool's errand at those geometries. So this is, you know, again, why do you think 3D NAND is on the market? This is why, right? The scaling up above here, just on technologies, gigabytes per square centimeter. I know Bob and some others use the square inch thing. I prefer square centimeters. I mean, what the heck? Although we are in the US, maybe I should use square inches, but it doesn't matter. You know, getting down below 16 nanometer, even planar TLC, there's quite a bit of diminishing returns, as you can well imagine. I mean, how small is small, right? How many electrons can you store in a cell without it becoming a random bit bucket, right? And then A, you don't have a storage device. B, you might as well go home because you just spent $10 billion making a fab that makes crap, right? So we're not going much lower, that's for sure. So what do we do? Well, let's start addressing in the Z dimension. Again, this must seem obvious to everybody, but literally this is the only way to get greater densities. Now, in the same square area footprint, obviously, Yes, the die packages are somewhat smaller or somewhat larger, but microscopically so. And as you well know, NAND for years has been assembled into packages. They're not just single die sitting on an SSD or on a flash module. They're 2 high, 4 high, 8, 16. Some folks are trying to do 34 and 64 die packages, which are quite large, right? Which is over and above, the mechanical packaging of this is over and above the 3D nature of the cells themselves. So, gigabytes per square centimeter, again, as you can see, tiering both in terms of number of layers and then also density or number of bits per cell, right? And as you might imagine, and I'll start talking about this in a little bit, there are technologies beyond TLC. Probably no secret that everybody is working on those, so-called QLC or 4-bit per cell. It's a hellaciously interesting problem. Because now I have 16 voltage levels floating around in there, floating, haha, you should get that as a floating, NAND person. But 16 levels, right? That's the good news and the bad news. Because how do you discern the very small minutia between these voltage levels and still figure out if the cell represents a 1 or a 0 and what state it's in? So this is a tougher problem. I have not heard anybody working on 5 bits per cell. Right? I know all sorts of folks that are working on 4 bits per cell, though. So maybe maybe 5 bits per cell will happen in my lifetime. Probably not. I mean, I'm an old fart, kind of. 27 years in the industry, and that figure is hexadecimal. So you do the math. Right? But the cost projection is the other reason why we're doing this. Right? Again, planar TLC, densest planar stuff we have, and anybody else has for that matter. Again, this is why the cost of this material isn't shrinking, right? We literally can't make it any denser. And if you run fabs, if you can't make it denser, you can't reduce the cost per bit. Sure, there are various manufacturing techniques you can try and be more efficient in the fabs. That's increase the yield for a few percentage points. That's all well and good, but it gets really difficult at the end of the day, right? On the other hand, right, cost per gigabyte, and this is kind of log scale, right? As you add tiers, there is this interesting effect. Now, some of the marketing folks would claim, oh, we're back on Moore's Law now that we're at 3D. No, I'm not going to say that. But we are back on a fairly predictable log scale that we can look at the costs going down and the density per die, density per wafer going up. And that is a wonderful thing because we all like our cheap storage, don't we? Confess, right? We love our cheap storage. I mean, after all, things like this, right? Things like this, consumer-oriented storage passed enterprise storage a long time ago in terms of number of bytes consumed, a long time ago, and the curves are divergent, right? Because of the prevalence of these things. There are, more mobile phones than people on the planet now, because you and I have more than one of these, or if you have 20-something kids like I do, yeah, raise your hand, they have multiple things. Right? And these are storage devices in disguise. It's awesome, right? More storage. We like that. So, imagine a world where, you're holding a 2 terabyte phone. It will happen. There's no question about it. And then the problem becomes bandwidth. Right? We should be having conferences on large bandwidth systems instead of large density storage systems. Because we can store the bits. It's like Doritos. We'll make more, but we need a way to get the bits out of there. So, or in, take your pick. So this is really interesting, right? So today, again, a single die, a little bit bigger than a square centimeter is 384 gigabits per square centimeter. So how many square centimeters to a square inch? Do the math, 6 and change. So we are over the 2 terabit per square inch mark right now, right? With TLC, right? MLC a little under, TLC a little over. Right, but that's today. Right, this is a goal of many in the flash industry is, a terabit per square centimeter. And then again, do the math, now we're 6 and change terabits per square inch. And then again, I can vertically package those in a stack, 4 high, 8 high, 16 high. Again, 32 and 64 high is a big challenge. It's hard to build that, right? Easy to talk about, hard to build. So this is where we're going for density. Again, we're right here, a little over 2 terabytes or 2 terabits per square inch, and we're getting toward 6 and change. So a near tripling here in a few years. Now, how many years is a few? Don't know. Right? We'll see how it goes. But that's a goal of the entire industry, is to get to terabit densities. No question about it. Right? Because we like our cheap storage, and we like to store our photos and videos. Ask the folks at the hyperscales who store all of this stuff. And I'll talk about very dense storage in a little bit. Because it's a big problem, pun intended. It is a massive problem. Right? And one of the speakers before is speculating. So, kind of little known fact in the flash industry, right? We talk about, well, you know, flash is very dense, and I've got some charts to show you and spreadsheets and whatnot. But if you added up all the bytes consumed, right, on an annual basis of all forms of persistent storage, so I don't count DRAM here, although buy more DRAM, Micron needs the business, Lord knows. But persistent storage, right, of all flavors, NAND flash accounts for, on a good day, 6% of that total. That's it. Right? So if you could wave a magic wand and say, okay, bing, now we have 12% of the world's bytes as NAND, we'd be out of fabs. Very simple. We'd be out of factory. You can't do that. Right now, if you have $50 billion lying around, we could make more fabs, and they take about, you know, year and a half, 2 years to start up. Wafer number one out the end of the, you know, out the back door. So this is not an easy industry, right? Somewhat similar to the hard drive industry, except about 10 times harder, as it turns out. Because, you know, a lot of people think, well, NAND is just kind of endless, right? I mean, there's so much of it, and the market is oversupplied, and, you know, other BS things like that. No, it's 5 to 6% of the bytes. That's it. Right? I wish it was 20% of the bytes, but it's not. So we'll get there. If we can go 1% a year up, wonderful. That would be great. Okay. So again, what's driving adoption? So we know what's driving adoption. Actually, it's you and I, and it's the consumers of the world. Never mind the enterprises. It's the consumers of the world that are driving flash adoption, because number one, you know, smaller devices, handheld devices, phones, tablets, all sorts of this. And then the whole other world that you never see, which is embedded. Right? Every single aircraft, every single automobile, every single ship floating on the sea contains lots and lots of persistent storage, mostly NAND, usually not rotating at all. Right? Very difficult environment for a rotating disk. Nothing against a rotating disk. I worked for a division of Seagate years. I may be one of the few people that had actually worked for all three technologies. I worked for Storage Tech for the better part of a decade. I worked for a division of Seagate. Now I work for Micron. So we got the trifecta going, at least. Right? Disk, tape, and NAND. But the adoption is driven from the consumer level up. Right? Because, you know, there's a lot of laptops open and MacBooks and all sorts of things. I'll bet more than half of you do not have a thing that rotates in there. Right? I mean, I nothing against rotating drives. I wouldn't buy a laptop with a rotating drive anymore, just won't. Maybe external, okay, but not inside. Certainly not a tablet with it, certainly not a MacBook Air in it. You can't fit the damn thing in there anyway. So this is what drives adoption. The enterprises are usually the last to take a technology. Let's face it, because, you know, if you're Bank of America or you're Shell, you have a wonderfully large battleship that you have to turn to adopt technologies like this. And you have funky things like change control boards. Imagine that, right? Little hard to take a technology. Anyway, so this is Gartner, so take it for what it's worth. You know, they're one of several research firms. And they're plotting out here 4 years, starting last year, this year, where the highest available capacity drive is going. Now again, NAND's in lots of forms. There are NAND that are not in a drive format, flash modules, and lots of companies make those. We supply NAND to lots of companies that make flash modules. And it's all great, but if you consider a drive form factor, so for HDD, it's our friend, the 3.5 inch, right? For SSDs, this is actually a bit of apple and orange because this is a 2.5 inch form factor, not a 3.5. Right? I'll talk about some, you know, enterprises and then some hyperscales as well are literally begging the industry to make a 3.5 inch form factor flash drive. And the question is, well, do you make one of those or do you make a flash module that kind of doesn't look like a drive form factor at all? which is on the table now. 5 years ago, that was completely off the table. People couldn't imagine something that I couldn't, put in a server slot. Well, now they can, which is really interesting. Right, so there's a very compelling TCO, and I'm going to get to that in a little bit, but you can see the progression here. Now, this does not try to project on beyond that, because if HAMR actually does its thing, we'll get way denser drives than that, and that's great, bring it on. If we can get HAMR to work at good cost and at scale, wonderful. I'm all for it. Same way with high capacity tape, but this is where Gartner thinks the drive industry is going. Right, again, as was mentioned before, today, 2.5 inch, 15 millimeter high, 15 tera, right, that's on the market right now. Right, and that is the first of much to come. So, and the reliability is very, very good on these. Number one, because there's a lot of die inside, and I can do things like RAIN, right, R-A-I-N, kind of like RAID, except spread them across individual flash nodes or dies, if you like, and then all sorts of forms of erasure coding, both at the host level and then the cluster level. Ceph was mentioned, good example of that. So very high reliability, very dense. Haven't talked about power and cooling a little bit, but we will. And it's interesting to note in the media industry, there are a lot of comparisons which people will try to put out there. It's like, oh, Rob, what about compression? Well, geez, I can compress data on anything. So that's kind of a wash. Rob, what about the network? Well, you got to have a network. So it's a wash, right? What I'm trying to focus on here is, number one, the media, and number two, how you package it. It actually makes a big difference. Okay, so not a statement of roadmap, but if one envisioned a target platform for QLC or very dense TLC, take your pick, doesn't have to be QLC, this is what it might look like. Right, again, trying to focus on what does it look like in a server. Never mind what does it look like in one of these to get to 10 terabytes in a handheld. Right, so number one is cost. And if you don't believe me that cost is an important factor, come with me and visit customers. And nearly the first question is, after, roadmap is cool and that's all great, it's, oh, well, Rob, how much does it cost? Can I afford it? And that's a very important question, right? Because if you can't afford it, I don't care if you got the best widget in the world, doesn't matter, people won't buy it. They won't, can't afford it. So cost is very important, so under $100, a tera. Have to be there. Kind of looks like this, but it could be different form factors as well. One can envision a 4U with lots more 2.5 inch slots, or maybe not a server form factor at all. So it gets interesting, right? But one of the goals that I certainly have as part of the industry is I want to get to at least a petabyte in a rack U, if not more. Right? So one of my goals envisioning, again, a few years out, is to get 3 petabytes in 2 rack U. So I'm going to say that again, 3 petabytes in 2 rack U. So do the math on how much you can put in a 42U rack, right? Multiply by 21. That's where we're headed. Right, now whether this is a good or bad thing depends on your point of view, right? But this is where we're headed, make no mistake. Right, because people will consume this, and I say that indirectly. Right, because when you send your photos up to Instagram, they have to go somewhere, right? The bits have to land somewhere. And the somewhere they land is the equation we're trying to solve. Right, because right now you can go read about it. I mean, secret, so for example, Facebook, their coldest of the cold tier is this Blu-ray jukebox library that they designed from scratch. And guess what? It's all of 1 petabyte per rack. I give up. Right? Now, 20 years ago, that was mind-bogglingly dense. Today, it's, are you kidding me? Right? Because I want to get 3 petabytes in 2 rack U. Right? So again, if you're a hyperscale and your biggest expense is building data centers, and believe me, it is, go visit them. There's 5 big ones in the US, there's 3 in China. Go visit, see what they do. Right? Data centers are a money pit. They're an absolute money pit. So the more they can squeeze out of that, the better. This is their whole rationale. Right? So NVMe, right? You can debate the interfaces all day long, but at this scale, I like serial ATA as much as the next guy, but you'd be, drinking the ocean through a straw. It doesn't work. Because I'll say the word migration here in a little bit. right? Which is the big bugaboo for some of these technologies. But anyway, so, you know, lots and lots of reads, write seldom, not once. I mean, the whole goal of archive storage is it's the holy grail, right? Write once, read never. Warn. And then I would argue, well, why in the hell are you writing in the first place, right? But people like their archives, so okay, I get that, right? I'll try to make something for you. Right, so again, you know, envy of me, PCI now. With these I/O sizes and, you know, speeds and feeds in and out of the box, so, you know, we're at Gen 3 right now. Our friends at Intel say Gen 4 is what, year and a half, you know. Pearly Skylake and beyond, and all the lakes. I can't remember. It's like Ice and Kabi, and I can't remember them all. But anyway, it's one of the lakes out there. But it's PCI Gen 4, PCIe Gen 4. So that's great. So, but look at this, you know, right? 500 sequential fills over life. Now that's a lot of data, because these drives are really dense, right? 64 terabytes per 2.5-inch 15 millimeter. 64 terabytes. That's where we're going. Right, so if I fill it 500 sequential fills, this is 32 petabytes total bytes written, right? Which, by the way, is a much more accurate way to describe a flash drive, is total bytes written, right? Drive rates per day implies some sort of daily average, which you and I know is, the technical term is bullshit, right? Workload goes like this all the time. So total byte fill or total bytes written is a much more accurate way to describe a device, I think. And you got to have a lot of throughput in here, so fast networks are great. And then, you know, at least 3 levels of data integrity, at least, for my money, right? Drive level range, so doing, you know, parity around inside the device, because I have lots and lots of die here, which is great, right? More parallelism, more on-feed channels, all that good stuff. And I want to distribute the data inside the drive, right? Kind of unbeknownst to the OS. Right? Then at the host level, or one of these, I can do error coding, or excuse me, erasure coding on that, which is great. And then I can also do cluster-wide erasure coding. Again, because, you know, if you're doing an exabyte of storage, the last thing you want to do is store 3 exabytes of storage. Right? Because we come right back full circle to, can I afford it? Right? So erasure coding is a very good thing. Okay, so I'm going to switch out of this. How much time I got left, Matt? Okay. Let's do this, if this will come up. Here we go. This is a spreadsheet. I'm going to zoom it down a little bit. I know you probably can't read all the numbers, but here's something I did, and I did this a few years ago, and this is for a real live customer. So let me give you a bit of a framework here. Real live customer, and all the data here in the colored bars are questions that I ask, right? Being a tape guy from way back. So I have a questionnaire which is like 35 questions that I'll put in front of a customer, and I ask them all sorts of weird and crazy stuff about their usage of tape. Right? Now again, nothing wrong with tape. Tape been around a long, long time, still going to be around a long, long time, so don't quote me as predicting the demise of tape. Not going to happen. Rotating disks, same thing. IBM RAMAC Model 305, anybody? Yeah, it's down in the Computer History Museum. Pretty cool, right? 50 platters! And to think Google wrote a paper a little bit ago that's kind of urging us to get there again. No, I don't want to do 50 platters anymore. Thank you. But that drive is now 60 years old. It's happy 60th birthday RAMAC. Right, so very interesting machine. Go see it. It's really cool. Well, anyway, so I ask them a whole bunch of questions, and they give me the data. Right, because the last thing I want to do, you know, as a CTO, is make up some data that I carved out of thin air and you know what piece of the anatomy, right? Not going there. This is customer data. So how much do you spend on HSM software maintenance? Right? How much do you spend per fiber channel switch, and how many of them do you have? Right? Because, you know, tape infrastructure is not about the cartridge, it's about everything around the cartridge. And that costs money. Right? So I'm trying to do a reasonable TCO based on customer data. This is an example of it. Now, they're not that large. They have 10 petabytes today. They ingest about 2 petabytes annually. Their numbers. right? This is their model, right? They have more than one library, so they have 2 sites with 2 libraries, all that. Oh yeah, Boink is telling me to do something, I don't care. So, and then all sorts of these, again, these questions with dollars and cents and facts and figures and cooling and power and cooling, which is really important. How much do they ingest? What does it cost? All this stuff goes through. Right now, I'm not going to spend a lot of time on this slide, but I also do migration. So if you had to migrate that 10 petabytes plus 2 annually, so the flow doesn't stop, and you had to migrate it to some other tape technology, what would it take? Right, both in terms of dollars and cents, but more importantly in terms of time. So we do the math, right? And then for the piece of resistance, as they say, there's actually math, arithmetic involved. So this is what it costs this customer to maintain their archive on $1 per petabyte per year basis. This is both CapEx and OpEx, right? And depending on what customers you talk to, CapEx is really important, and then other customers, OpEx is really important. All right, because if you're a hyperscale, OpEx is everything, right? CapEx is a rounding error. They can buy any damn thing they want, right? But running it at scale takes a lot of money, right? On the other hand, enterprises, right, they're scared to death of CapEx. They don't want to spend a dime, but they got all sorts of money for OpEx, no cash flow, right? No problem, right? I got cash. So it's a different story for different strokes for different folks. So it costs them a little under $500K a year per petabyte, actual customer. And again, this is based on their own numbers. Day 0 cost, and then 5 years of maintenance, 5 years of power, 5 years of admins, all that good stuff. And then there's this. So this is scale-out NAS, or using rotating disk and scale-out nodes. And there's a lot of clustered file systems that you use. Take your pick, right? And again, I'll zoom this down a little bit. But there's 5 years of power, and the cost of power is significantly more than tape, right? Significantly more than tape. Almost $300,000 to power the damn thing. 5 years of power for tape, 83. Mostly of the stuff around the tape. Right, the servers and the fabric and all that stuff. So this doesn't consume a lot of power, but it's a lot of CapEx. So notice that it actually does cost you more to run, or for this customer, it would cost them more to run scale-out NAS with rotating at these parameters, which are very common. And I plug in any parameter I want. 60 drives a node, 10 tera, so fairly deep rotating, and you can see the rest. Right, and by the way, a 70% discount off of list. That turns out to be important. Right, so negotiate with your salesperson. Lesson 101. Right, because that determines what you're actually going to buy it for on the street. So finally, here's SSD. Right, now again, look, if you assume the existence of a 32 drive or a 32 terabyte drive, and you can plug in any number you want. Right, smaller numbers don't make as much economic sense as larger numbers, of course. But using that model, which I just showed you, right? And again, a certain, list price, $600 terabyte, really expensive, and then you get a discount, right? And how many nodes you got to add, and the cooling costs. Again, I'll scale this down a little bit. There. So for this customer, all in, fairly big year 0 cost, but because it doesn't suck down a lot of power because it's not rotating, I end up with that, which, by the way, is under the 5-year TCO for tape. And well under the 5-year TCO for scale-out NAS with rotating. So that's this customer, based on their data. Okay, so you can quibble with the data, you go argue with the customer, not me. So let's do, so that's 10 petabytes plus 2 per year. Okay, and you're saying, okay, Rob, well that's cool, but, right, I'm at exabyte scale. And I mean an exabyte. Which, by the way, is a shit ton of data. It just is. Right? If you've ever visited a data center with an exabyte in it, you know what I'm talking about. An exabyte is a fearsome thing. Make no mistake. In any technology, it is a fearsome thing. Right? So, again, here's that. And this is, top of the line tape libraries, world's best monsters, right? And you can plug in a number, right? The customer estimated $1 million. Okay, fine, $1 million. I don't care, right? And then all the other numbers are kind of corresponding. 8% for library hardware maintenance, 7.5% for library software, 8,000 new cartridges a year. a certain cadre of tape drives, 50 in the first library, 40 in the second. The power is the same. Lots and lots of SAN storage, a petabyte in front of an exabyte, that's their rule of thumb, right? 3 orders of magnitude. So you can guess how much storage they had in front of their 10 petabyte archive, right? Answer, 100 terabytes, right? So that's their math, right? And they add, 200, if they went to exabyte scale, they'd hold an exabyte and add 200 petabytes a year. And as you might imagine, the dominant cost in this is the cost of the media. Right? At smaller scale, 10 petabytes, the dominant cost is not the media at all. It's everything around it, right? Here is the dominant cost is the media. Make no mistake. Right? So again, using their own figures on price per cartridge and library and drive and maintenance and all that stuff, the migration is ridiculous. Right? So if they busied up all their drives, you scale that down a little bit. So they have 50 in one library, 40 in the other. So 40-40, right? The other 10 are doing nothing or ingesting, right? 40-40. At this rate, which is very common in the industry, 31 years. I'm not going to be around in 31 years, literally. Now, some of you young punks might, but not me. Not going to happen. So anyway, we did that, and lo and behold, even though the media cost is dominant here, costs you a lot for the cartridges. So this is an exabyte, remember, and it's a big number. So they're going to spend, almost $700 million over that 5 years to hold and run and operate an exabyte. Right? Building is one thing, operating is another. Right? But it works out to be about $413. Not bad for 2 sites. Not bad. Right? And again, you can see that, $60 million worth of libraries, drives, but cartridges all over the place. Gazillions of cartridges. That's a technical term. So here's NAS. NAS is higher. Right? Less CapEx, but boy, do you pay for the OpEx, because over the 5 years, you pay $29 million to run the thing, just to power it. And cool it too, because, heat is a funny thing. You put a watt in, you got to take a watt out. So who knew, right? And lots and lots of kilowatt hours or megawatt hours if you prefer, but this is basically a 3 megawatt approach. That's about what it takes. And again, the last slide here, I promised, man. Here's SSD. SSD considerably lower. Because again, while the media might cost a lot, right, the OpEx comes out in favor, so it's under 400 grand a petabyte a year to operate. With, again, assuming dense flash, you can put any number in here you like. Right? It's just a spreadsheet, it's just arithmetic, right? But again, using customer data, if they scaled to an exabyte, which they're nowhere near, right? But they wanted to do the exercise, right? Because to see the effect of very dense SSDs, because they want to know, right? 5 years from now, how should I build my archive? They want to know, because they don't know, they might take that much data in, maybe not, but that's the way it looks. So, okay. I think I'll entertain questions, or am I done? Sure. You bet. Yes, sir.
So Jim Handy's predicting
I know Jim. Tell him I said hi. He's a good guy.
Doom and gloom because in his expectation with 3D NAND we'll have a glut of supply and demand may not be able to keep up. Tidman saying if we don't get a 35% year-over-year increase in demand, that the industry is going to suffer. So what is your position on this, and how do you see demand actually, like what are the sources that are going to cause demand to really increase beyond what we've seen so far, which is actually pretty strong, but not as strong as maybe 35%?
Well, it's kind of be careful what you ask for, I think. Again, there is kind of the basic equation of, how many fabs do we have to build to meet the demand today? And the answer is we're kind of right there. We have a good number of fabs to satisfy, the 5 or 6% of the world's bytes shipped, right? Which is about all we can make right now. Now, you can do the math, and 30% a year, but again, NAND in particular, I'll leave DRAM to the side, it's a different beast, but NAND in particular, The demand is driven, again, kind of from the bottom up. You know, you can speculate on count on one hand the companies that make this stuff, right, including mine, right, and how much is consumed in devices like this. It's a lot, right? A lot of NAND goes to mobile. A lot of NAND goes to embedded, right? We love our refrigerators with IP version 6 addresses. Who knew? But they do, right? And thermostats with memory in them, and they do. So things like that. So more NAND is getting consumed from those, you know, channels, if you like, rather than just, you know, hey, big bank, big oil company, enterprise, right? Much more is consumed here. So the demand for this is just seemingly insatiable. It really is. It's ridiculous. But it also, just coincidentally, happens to meet also the cost per bit that we, the NAND manufacturers, are able to make the stuff. Again, because A, we love our cheap storage. So B, that's rule number 1, 2, and 3. We love our cheap storage, so we have to keep it very cost competitive. So if you assume that, then I think the growth profile for 3D NAND is very healthy. Very healthy. There is this stair step function, A on density, right? We're going to go from 2 to 6 in a big hurry, right? This is, you know, if I get a 1 terabit inside a square centimeter, that gets really interesting in a big hurry. Again, and this will be, you know, 2 terabyte mobile phones, right? Which people will buy, assuming the price is right. So I think the demand is going to be there, especially for NAND, because again, you could talk about, you know, HDD replacement and tape replacement. That's all great, but that's a fraction of what the world is doing, right? There's one company that might consume almost half its NAND just for its mobile business. Right? That's a lot, right? So they want to be number one in mobile phones. Well, they got to have NAND to go inside of that. So they either make it or they buy it, one or the other. So I think the demand profile is, you know, I love Jim. He's a great guy. I think it's healthier than you might imagine. But again, it's somewhat constrained because the cost of entry into a fab is very high. Right? This is not for the meek. You know, these are 10-figure investments to do something like that. And then they produce for quite some time, so they're worth it in the long run to do. But you better be right if you build one of these things. So very good question. Matt, I'm done. Thank you, sir.